Hello. Today I'm going to talk to you about building reproducible machine learning pipelines using Buildkite. And just to introduce myself, my name is Andy MacKinlay. I'm a tech lead of the NLP team at CultureAmp. What NLP means and what CultureAmp does, I'll talk about in a moment. But I came from a researchy PhD background in natural language processing quite a long time ago. And I've then moved into more of the industrial research space, also in machine learning and NLP. And now I've found myself the last few years at a product company building machine learning and specifically natural language processing tools. So, who is CultureAmp and where do we sit there? So CultureAmp is an employee experience platform. So companies pay CultureAmp to use our tools so that they can make lives better for their employees. There's a few different tools that we have, as I'll explain in a bit more detail later. But as to where I sit, we're in the data intelligence camp, which is the division in CultureAmp that specializes in getting the maximum value from our customers' data and eventually feeding those insights back to our customers to make their lives better. And within the data intelligence camp, I'm in the natural language processing team. So we're a complex subsystems team. We build APIs that sit behind user-facing products to run natural language processing tools over the textual data that comes from our end users mostly. So, machine learning. What is machine learning? I think a lot of people have a better idea now than they did a few years ago. But just to make it explicitly clear, just talk about it by example. The classic example being, of course, the hot dog or not hot dog identifier from the TV show Silicon Valley. So in this case, the machine learning problem is that we have some sort of unstructured input being an image here. And this is how machine learning usually works. We get some unstructured input and we produce some structured label for it. Sometimes other things, but often it's a structured label from a predefined set. Here, the labels are hot dog or not hot dog. So the input is that image, and the output is just a hot dog or not hot dog label. So the reason we use machine learning here is that it's usually quite hard to encode this using traditional sort of procedural programming techniques. We could, in some of these examples, count the number of red pixels and make a guess about whether it's a hot dog, but that is not an approach that's going to be very robust and accurate and generalizable in the whole world of images that we could actually see in the real world. So that's where machine learning comes in. But how, I hear you ask, how does machine learning come in? I'm just going to get rid of my face. You can see out my slides are probably more interesting than my moving mouth parts. So the way that we actually do machine learning, we use these things called models. Models are essentially a collection of weights of floating point values, and when we do inference in machine learning, we have an algorithm which combines the unstructured input with the model weights to produce some label. So here I'm moving to examples from the NLP world because that's the one that I'm more familiar with. That's the one that the work that I'm talking about happens to be in the NLP kind of subfield of machine learning. So we take this, here we have this unstructured text input. Our inference algorithm here is a sentiment classifier. It does some it combines those weights, as I said, with this unstructured input and produces some label. Here it's a positive sentiment label. So we're asserting that this text is talking about something positively, and it says this place is awesome. That's probably quite a good assessment, right? So there are obviously lots of things, lots of classifications we could do in supervised machine learning. I'm not talking about unsupervised here. In supervised machine learning. And so another thing we could look at is the topic of the text. So they mention they pay me way more than I'm worth. So it's uncontroversial probably to think this text is about salary in the context of a comment on an employee engagement survey, which this is supposed to be an example of. So this model artifact is a collection of weights. How do we get them? Where do they come from? How basically does supervised machine learning work? Well, this is how. So we have a collection of training data. That's kind of the secret source of machine learning. We need to have some data to actually learn from. So here we've got textual data for training a sentiment classifier. You'll see we've got the text, and we have the probably some human annotated label for what the sentiment is associated with that text. So I've got 5 rows here, but in real examples, we'll have anywhere from hundreds to millions of rows. We feed that into a pre-processing algorithm. After we've done whatever pre-processing we need there, we feed it into a training algorithm that learns the weights and dumps them into some kind of model artifact where it can be used at inference time to do the process I described previously, where we take the unstructured input, combine it with the weights, and produce a label. And this will come up a little bit later. We'll also know that lots of different parameters are important to this pre-processing and training process. So this training process is how we produce models. Those of you who are listening to this talk probably come from maybe more of a DevOps background, and if I've talked about can we automate the training, you'll probably say yes, sure. We just run the training code. And while that's largely true, there are some additional complexities to doing that compared to, say, a conventional CI/CD pipeline. And one of the key differences there is that the training process relies a lot on data, which adds just an extra dimension of things that can change and go wrong. So here's my highly technical diagram. Our pre-processing code puts data into our training pipeline. We filtered it some way to create the training data. Our training code then pre-processes it and outputs a model. So automating the model training is kind of part of MLOps, which is basically DevOps as applied to machine learning. And there are other facets of MLOps like model monitoring, which I'm not really covering in detail here. But the automation of things like model training is somewhat behind where we are in the regular software world, partly because of the complexity and partly probably for some other reasons. So there are still a lot of training pipelines that get run in sort of ad hoc fashion on individual kind of pet instances, be it developers' laptops or cloud notebooks, rather than in a repeatable, automated way. So going back to why model training is not just doing a build, there are lots of reasons for that. So the data, as I mentioned before, is a key point. So it's a really important input to the model building. It can change over time because we get new information coming in from users or from manual annotation of that training data, like our sentiment labels that I showed before, for example. So the data can change. Even if the data doesn't change, we might need our model to change. So we might have no extra training data, but suddenly, say, COVID has happened, and our topic classifier would say we'll be producing the same outputs if we haven't retrained it. But the things that people are talking about in employee engagement surveys pre and post-COVID are presumably going to be somewhat different. Concerns about remote work are probably much higher post-COVID. Another sort of minor difference is that the training process tends to take more time than a classic CI/CD pipeline. Can take hours or more. So it's not just a half-hour run tests and do a Docker build. But also the fact that there are lots more dimensions of variation. So in when we're training a model, it's not usually just a Boolean decision of yes, no, this model works or it doesn't work. What we get when we're training a model is some accuracy metric. We get an accuracy metric by running a model over an unseen data set where we have a notion of what the true labels should be. We see whether the model outputs match those true labels, and we get a measure of, say, the model accuracy. Now, when we get a number for accuracy, it won't be 100%, and it's hopefully not 0%. It'll be somewhere in between. We don't really know when we are done. Often done is sort of good enough from a product perspective, but what we really don't know is, can we do any better? One of the ways we might try to do better is by changing the parameters. So there are lots and lots of parameters. Here we've got a few. Got the number of training epochs and the batch size and the learning rate. Now, all of these are parameters to the learning algorithm. We can also have parameters to the pre-processing algorithm. And all of these things can have an impact in a positive or negative way on the final model. And we don't really know in advance without trying it which ones are going to work. So obviously, and the other thing, of course, is these parameters can can interact with each other when you change them. So you get a combinatorial explosion of possible ways to train a model. This is one reason why we want to be able to automate the training process as much as possible and have it predictable, so we can easily rerun it with a different set of parameters for either experimentation or for a production model training run when we know that a particular set of parameters are likely to be better. And that will usually happen at the end of an experimentation process or some kind of hyperparameter search. The key part is that we want to know which parameters a given model training run was produced with, so that we have and track that over time. Okay, so that's kind of the context of machine learning and MLOps, just to take a little step back and think about why Culture Amp is doing machine learning, in particular NLP. So the work that inspired this, it kind of sits over on the left there in the engagement survey space, where we're working on our sentiment model that we use to produce this aggregate bubble chart view of which comments are negative, neutral, or positive in nature. You can also see that there's a topic classifier that's used to derive that, which is why we have collaboration and work life as bubbles there. But we have lots of other textual data as well. We have building development plans for how you want to grow your career, and we have performance management, where managers leave detailed performance reviews for the direct reports. And these are other ripe future areas where we may wish to apply natural language processing in the future. So we want to make sure we're good at automatically training our models. So as to Culture Amp's tech stack, so Culture Amp uses Buildkite very heavily. We have hundreds of build pipelines, and I think the setup is reasonably standard. Buildkite detects changes coming in from GitHub. In our continuous integration account, we run our Buildkite agents, and they run all the appropriate CI/CD bits and ultimately deploy apps. Here we've got Fargate apps to kind of user-facing accounts like production, where the user-facing services are, or development accounts for internal use that obviously mirror the production accounts. These web apps are going to connect to a database of some kind, presumably as well. So that's fairly standard. Now, no Buildkite involved here. We do have a data lake at Culture Amp, which aggregates and combines the data from the production databases into a form that's usable for data science, various forms of ad hoc experimentation, and of course, machine learning model building, as we'll see in a moment. So there's a tool called DBT, which takes the data from these production databases, applies transformations to it, and outputs that transformed data into S3 buckets. We then use this query engine called Amazon Athena that can take the data from the S3 buckets and overlay a query engine that lets data scientists add automated training scripts, etc., query the data using SQL to put it into a format that's usable for whatever ever task we're involved in. A lot of the interaction with this is in cloud notebooks, SageMaker notebooks, where we can do ad hoc experimentation with a human directly interacting with Athena. But that is kind of the thing we want to move away from for the cases where we have a model that we depend on in production. So rather than having code in a Jupyter notebook, we keep Drake happy and have reproducible training pipelines using kind of the existing CI/CD tooling that we're using at Culture Amp as the first pass. If that does the job, and Buildkite is a very flexible tool that can do lots of things, then we're going to have less friction than building something else from scratch. So we're trying to reuse Buildkite as much as possible in this work. So what we want is basically our training code is versioned. We know exactly which parameters and which code were used to produce a given model. We want to have tracking of the ID of the model, which I'll show you in a moment. We want to have it train when new code is committed, train on demand, and ability for humans in the loop to inspect the accuracy of the model before we make a decision about whether to actually deploy the model after the training phase. So we're using GitHub and Buildkite, as already mentioned. Also, AWS Batch, which you may or may not be familiar with. It's a tool for running arbitrary containers as one-off jobs in AWS. And then Metaflow, which is an orchestration tool for commonly used for Python workflows, which is quite common in the machine learning world. The other one that's relevant for this talk is weights and biases, which is used for tracking machine learning training, basically machine learning experiments. Okay, so the architecture of the training. We have our same Buildkite agents. They trigger the training not in a production account, but in the data lake account in this case. So we have the training runs inside AWS Batch. And specifically, it runs on Metaflow. Metaflow orchestrates the training by querying Athena and then learning the weights based on the data that's pulled from Athena, and pushes the outputs of that training process, the model artifacts, into an S3 bucket where it's available to use later at deployment time. We also run some evaluation of that data of the kind I talked about, where we compare it against some human annotated data set and write those statistics into weights and biases, so where we can manually inspect it. I'll show you how that works soon. So here's the kind of step diagram for the training. So a user makes a change to the training code. GitHub sends a notification to Buildkite, which triggers a training run. Inside Metaflow in the data lake, we query for the training data, we run the code, we run the evaluation, store those results in weights and biases, upload the model to S3, and send a notification back to Buildkite that training is complete. So how do we communicate back to Buildkite? Buildkite has an API. I had never used it before, but I posted in our helpful Buildkite support channel, and I was pointed to it. So we can talk back to Buildkite to do interesting things, and I'll show you specifically how that works in a moment. So once we've talked back to Buildkite, we can inspect the results in weights and biases, and then make a decision about whether to deploy it or not. So here is how our some of our interaction points with Buildkite work. So here's where we're triggering our training Metaflow job. on batch. Most interesting parts here probably is environment variables. Okay, one interesting one is the model ID. So we're using the fact that we have a Buildkite build number as a unique identifier for the model ID. So we can then use that to work backwards and work out which training code version was used, which parameters were used for a given training run. We're passing an S3 path for the interim model artifacts to be stored, and we're passing the name of another Buildkite step, which is the one that we want to unblock when our training is finished. We'll see that specifically in a moment. So on the right here, we are inside our Metaflow code. This is just Python code for the most part. In a prepare step, we fetch our data. We fetch our data based on the parameters, which are serialized inside the code base for the moment. And then we kick off our training step after we've fetched the data. Again, the training step also depends on the parameters that have been pulled out of the code base. And so we run our training. After the training is finished, we then say, okay, Buildkite training is done. You can do something with that information. So this is notify Buildkite step at the bottom here. And that passes through various metadata that's useful both for manual inspection and for subsequent deployment. So more specifically, here's the implementation of notify Buildkite. So we're pulling in the environment variable that I talked about previously, which is the name of the step, the key of the step that we want to unblock, as well as a build number we can use for querying. We create our Buildkite unblocker, and then we notify it, and we pass through this metadata. So the path where the model artifact is stored, the weights and biases run ID, which we can use for inspecting the statistics we've created, the environment variables, which are basically parameters we need for the model at deployment time, and a Docker image that we need to use for deploying the model. So you'll notice that these keys here match, of course, the keys in the Buildkite unblock step over on the right here. So model data path, weights and biases, run ID, etc. And that is of course, the training step that we've unblocked. Training finished, training_finished, as you can see there. So the implementation here calls using the Buildkite API, and then the step gets unblocked. I'll see a picture of that in a moment. So how does the deployment work? Deployment is somewhat simpler. So if we've chosen to actually do the deployment, we pull in the model artifacts, the tarball from S3 into Buildkite. We push it to where it's needed in the production accounts, which you can see here. And then once that's available there in S3, we can create a SageMaker endpoint, which is essentially an HTTP wrapper that knows how to run the model artifact, because we have a specific Docker image that's designed to work with the model artifact, and then it serves it up behind a web API, which we can then use and call in production. Okay, so here's the kind of deployment flow. We make a decision about deployment, trigger the deployment Buildkite, request the model artifact from S3, push it to a different S3 so we can use it in production, and then create the SageMaker endpoint that references that S3 bucket, and also the Docker image that we receive from the callback to the Buildkite step using the Buildkite API. Okay, so here is the kind of the DAG of the full training and deploy flow, which you can get by appending /DAG to your build URL in Buildkite. So we have some bookkeeping. We have to build two different kind of images. We build two images because we want one that has GPU drivers built in, so the training is nice and fast, because we need GPU for our training. And then we have a default image that's much smaller that we can use for other steps. We build both of those things. We deploy the stack using CloudFormation, and then we run our Metaflow orchestrator Inside there, as we already saw, that will do an API call to unblock the training is finished step, and then we can examine the results and decide whether to deploy. So here's how it looks inside the regular Buildkite interface. As you can see, at this point, we're at the end of training. Training is finished. We've created an annotation to kind of put the link to weights and biases front and center. It's very easy for a human to see. This information is not really needed, but we just output it for debugging. But we do have a nice link here to weights and biases, where we can go and click through and inspect the accuracy statistics before we make a decision about deployment. So inside weights and biases, there's a lot to weights and biases, but here's the thing, something like you see when you click through one of those links, we get to see the accuracy statistics over a particular data set. These are not necessarily real numbers, by the way. These are put in for illustrative purposes. We can look at those numbers. We can compare them with other runs. We can compare them with experimental runs that were not run using the Buildkite pipeline as well, because the same code can be run basically outside of here, just directly inside SageMaker Notebook. And you compare against our best experimental run with the same parameters and make sure that the accuracy is what we expect. And then if we're happy with that, we can go and deploy the model, and that goes through the steps I outlined previously. Upload it to the right place and create the SageMaker endpoint, and then it's available in production. It's tagged basically with the model ID that was generated by Buildkite, so we have tracking over all time of which model was run, and every prediction gets tagged with that model ID. So we can always link a given prediction basically back to a given Buildkite run that was used to produce the model, which also can help us track down things that don't go as expected. Okay, so that is CultureAmp, a first pass at a reproducible training pipeline at CultureAmp using Buildkite. Come back to us in a year or two, and we'll probably have made a bunch of optimizations and improvements to it. This is our first go, so we probably haven't got everything right the first time, but so far it's working reasonably well. We're using this to actually actively deploy our most recent sentiment model, and nothing terrible has come up so far. So just some quick acknowledgements. The natural language processing team. We've got Anna, Elmer, Clint, Joseph, Pierce, and Uti. Shout out to Anna in particular, who did a lot of the Buildkite work that I've talked about here. And then some other colleagues from the data intelligence camp who provided feedback on the overall architecture or this specific talk. We've got the two Louis and Arwan and Isabel, who are all a lot of help there. So I'll just give you another view of my face before I say goodbye and thank you. And that is it from me, Andy, from CultureAmp. Goodbye.